Hi and welcome to this video on integration using partial fractions. We use integration by partial fractions where we have a polynomial in the numerator and a polynomial or the factors of a polynomial in the denominator. Let's just go over some algebraic fractions and some revision. So if we have 2 over x minus 3 minus 4 over x minus 1. We find the lowest common multiple, and in this case the lowest common multiple is x minus 3, x minus 1. And then we multiply the top by x minus 3, x minus 1, and the same on this side, x minus 3, x minus 1. On this side the x minus 1 cancels out because we've got a minus x minus 1 in the denominator, and on this side the x minus 3 cancels out because we've got an x minus 3 in the denominator. So this then becomes 2 x minus 1 minus 4 x minus 3 all over x minus 3 x minus 1. When we get rid of the brackets, multiply out, we get 2 times x is 2x, 2 times minus 1 is minus 2, minus 4x plus 12 all over x minus 3 x minus 1. Then when we combine like terms, we get 10 minus 2x all over x minus 3 x minus 1. Now when we do partial fraction decomposition, in practice the reverse process of this is required. So if we're given 8x minus 28 over x squared minus 6x plus 8, first of all we factorize the denominator. This gives us x minus 2, x minus 4. Then we assume that each factor gives rise to a single partial fraction. So 8x minus 8 over x minus 2 x minus 4 is a over x minus 2 plus b x minus 4. A and b are constants. Then we do as we did in this case, we get the lowest common multiple and multiply the top. So this would be a x minus 2 x minus 4, but because we've got an x minus 2 on the bottom, it's a x minus 4 over x minus 2 x minus 4 plus, and then the same here, we multiply b by x minus 2 and x minus 4, but because we've got an x minus 4 on the bottom, we're just left with an x minus 2, so this becomes b x minus 2 all over x minus 2 x minus 4. This equals a x minus 4 b x minus 2 all over x minus 2 x minus 4 using our laws of fractions. So in the numerator, 8x minus 8 equals a x minus 4 b x minus 2, and the denominator x minus 2 x minus 4 equals the denominator in this case, which was x minus 2 x minus 4. So in this case our 8x minus 8, which is our numerator, equals ax minus 4 plus bx minus 2. And from this we find the constants a and b. When doing integration using partial fractions, 3 rules to bear in mind. So it's the integration of rational expressions of polynomials. We have to check the numerator is not a derivative of the denominator. If it is, then we can use another integration technique. And then we check the degree of the polynomial of the numerator, that's the polynomial on top, is less than that of the denominator. So that means that the power x squared is sort of less on the numerator than it is on the denominator. So if it was x squared over x cubed, that'll be fine. If it's x squared over x squared, we have to use a technique to make the degree of the polynomial in the numerator less than that of the denominator. Let's go over some fraction decomposition. So if we had this factor in the denominator and then the term in the decomposition, so if it was simply ax plus b in the denominator, we would have just one constant a over ax plus b. If it was ax plus b squared, we'd have a constant a and a constant b plus, and on here we would have ax plus b, and below the b we'd have ax plus b squared. If this was cubed, it would be ax plus b over the constant b ax plus b squared plus the constant c over ax plus b cubed. If we have an x squared, so we have ax squared plus bx plus c, then we have ax plus b, so ax and then another constant b over ax squared plus bx plus c. So these three rules we have to bear in mind when we're doing decomposition and then choosing our factors. The other thing we have to do is, if we can, we make the denominator into a factor, like x minus 3 or x minus 2, and also try to make the degree of the polynomial less than that of the denominator. So we'll have a look at some techniques for that. Using the degree of the polynomial in the numerator is to use long division of algebraic long division. So for that previous problem, if we had the integral again of 2x cubed minus x minus 1 all over x minus 3 x squared plus 1. We saw that this became the integral of 2x cubed minus x minus 1 over x cubed minus 3x squared plus x minus 3. The degree of that is the same as that, so we want to make this less, so we use algebraic long division. So we set up our division. So our 2x cubed minus, now we mustn't forget any x squares, no x squared, minus x minus 1, and divided by x cubed minus 3x squared plus x minus 3. When we do this, we get a 2 on the top, and then multiplying through by 2 we get 2x cubed minus 6x squared plus 2x minus 6, and we subtract. When we subtract, this becomes 0. We're left with 6x squared plus 3x plus 5. And so our integral becomes the integral of 2 plus 6x squared plus 3x plus 5 all over x minus 3 x squared minus 1, x squared plus 1 rather, sorry. Now, for those of you who've forgotten how to do algebraic long division, let's just have a quick recap on a simple one, and if we follow these rules it's quite easy. So if we have x plus 3 and then x squared plus 7x plus 12. So that's a dividend, that's the divisor, the quotient goes on the top. So first of all, we look for these two x's, so x squared divided by x, that gives us x. I'll put the x on the top. Then we multiply the x by the x plus 3 and write that on the bottom here, which is x squared plus 3x. Subtract those two, bring that one down. Now what we do is we get we're left with 4x, and then when we bring that down we're left with plus 12. So we get the 4x and then multiply by the x, and we're left with 4. So we put the plus 4 on the top, and then we multiply the 4, which is here, by x plus 3 again, and we get 4x plus 12 minus that, and we're left with 0. So if we follow those steps, okay, an easier way of reducing the degree of the polynomial in the numerator, again using our algebraic long division but a quick method, if we have integrating 2x cubed minus x minus 1 all over x minus 3 x squared plus 1 dx. So we look at the 2 there, and we want to make sure that the degree of this polynomial is either less. Oh, here we go. Okay, a quick look at reducing the degree of the polynomial in the numerator. Again, this is by algebraic long division but a quick method. So if we have 2x cubed minus x minus 1 over x minus 3x squared minus plus 1 dx, what we do then is we check what degree the denominator is by multiplying out the brackets, and we get it's x cubed minus 3x squared plus x minus 3. So the degree of the polynomials are the same, so really we want to reduce the degree of the denominator. So we can either do this by algebraic long division or a quick method. We notice that when we do algebraic long division that we've got a factor of 2 involved. So what we do is we multiply 2 into this, which is our divisor in the long division. So what we get is 2x cubed minus 6x squared plus 2x minus 6. And as we did in the algebraic long division, we then put that on the top, the numerator, so we get 2x cubed minus, now we've got no x squareds, minus x minus 1, and we subtract, and we get 6x squared minus 3x plus 5. This is our remainder from our algebraic long division, and so this then becomes 6x squared minus 3x plus 5 all over our x minus 3 x plus 1, and we've got the 2 as well, which was what we multiplied by here, times 2 to get this. So this then becomes the integral of 2 plus that dx. So here we get a x minus 3 plus, now because of our x squared, we could have an x in our numerator, so we have to put a bx plus c, and we get x squared plus 1, and that is our algebraic fraction reduction, partial fractions reductions. So if we have 2 4x squared plus 1 over 2x plus 1 2x minus 1. So what we do is we can leave this 2 out, and then we're left with 2 constants, which would be a and b. We have the 2x plus 1 on the bottom here, and the 2x minus 1 on the bottom there. Now, as we did before with our now what we need to do is get the lowest common multiple and multiply the top. So this would be 2x plus 1, 2x minus 1, and the same on this side, 2x plus 1, 2x minus 1. So these cancel each other out, and this cancels with that, and we're left with 2 plus a 2x minus 1 plus b 2x plus 1 all over 2x plus 1 2x minus 1. Now we know that our numerator, which is the 2 4x squared plus 1 equals the numerator in this. So we can say that 4x squared plus 1 equals a 2x minus 1 plus b 2x plus 1. Now in this method what we do is we choose x to be something which gets rid of one of the factors. So if we choose x to be a half, when we have here x equals a half, this will equal 1 minus 1 0, so the a will disappear, and we will have b. Half times 2 is 1, plus 1 is 2, and here half squared is a quarter times 4 is 1, that's 2. So 2 equals b2, so b equals 1. Now if we choose x to be a minus half, again this side becomes 2. Our b disappears because minus half times 2 is minus 1, minus 1 plus 1 is 0. This b disappears and we're left with a. 1 times 2 is 2, minus 1 is minus 1. Minus 2. So our a equals minus 1. So what does this mean? Well, this means that this fraction on the top becomes the integral of 2 plus the integral of a, which is minus 1 over 2x plus 1, plus the integral of 1 all over 2x minus 1. And when we do that, we get 2x the natural log of 2 minus the natural log of 2x plus 1 plus the natural log of 2x minus 1 plus c. And that is our answer. The second method to find the constants when we're using partial fractions in integration is to use comparing coefficients. So if we have the integral of 6x squared minus 3x plus 5 all over x minus 3 x squared plus 1 dx. When we do the partial fraction decomposition, we get a plus, because of the x squared, it becomes bx plus c. So the a is over the x minus 3, and this is x squared plus 1. Then we do our multiplication with the lowest common multiple, and we get a x squared plus 1 plus bx plus c x minus 3 equals the numerator, which was 6x squared plus 3x plus 5. Now first of all, we can tackle this like we did before when we're finding the constants. We make one of the brackets equals 0, and that will make us just have one unknown left. So if we use x equals 3 in this first case, when we use x equals 3, this becomes 0, this whole term. So we're left with, here it's 3 squared plus 1, 10, so 10a equals, and then when we put x equals 3 in here, we get 50. So a equals 5. Now we can't do much because we've got another two unknowns, so let's use our comparing coefficients. So to do that we multiply all this out and we get ax squared plus a plus bx squared minus 3bx plus cx plus 3c equals 6x squared plus 3x plus 5. Now what we do is we collect the like terms. So we have a plus b x squared, so we can cross off this x squared here and this x squared, and then we look at the x's and we have 3b plus c x, and then we just have these a plus 3c left over, which will equal the constant 5 here. Now what we do is we look at the x squared here and we look at the x squared here and compare the coefficients. So this is 6, so here this will equal 6. So we have, when we're doing that, we have a plus b equals 6. We know our a is 5, so our b equals 1. If we want to know our c, we've got here 3c plus a is equal to 5, so our a minus 3c equals 5, and because the a equals 5, our 3c equals 0 and our c equals 0. So c equals 0, b equals 1 and a equals 5. So the integral then becomes a, which is, where are we now, 5 over x minus 3 plus our bx plus c, and our c was 0 and our b was 1, so it's just bx is just x over x squared plus 1 dx. And then when we do the integration, this is 5 natural log of x minus 3 plus a half natural log x squared plus 1 plus c. Integral of 1 over x squared minus 9 dx is a difference of 2 squares, so this then becomes the integral of a over x plus 3 plus b over x minus 3 dx. Now when we get the common denominator, add the factors and equate the numerators, we get a x minus 3 plus b x plus 3, and the numerator is 1. So then what we do is we let, in the first case, x equal minus 3. So a minus 6 equals 1, so a equals minus 1 over 6, and then x equals, let x equal 3, so we get b 6 equals 1, so b equals 1 over 6. We substitute this back into our integral, and we get 1 x squared minus 9 dx equals the integral of minus 1 6 x plus 3 plus 1 6 over x minus 3 dx. And then when we do the integration, we get minus 1 6 natural log x plus 3 plus 1 6 natural log x minus 3 plus c, and that is our answer. So let's have a look at a couple of more examples. Integral of x squared minus 1 over x squared minus 16. Okay, again we can see that the numerator, the degree of the numerator is the same as the degree of the denominator, so we need to reduce it. So how do we do that? Well, we can do that by algebraic division, and when we do that we get x squared minus 1 x squared plus 16, and we minus, and we get 15 as the remainder. So how do we express the remainder? We express it as 15 over the numerator, which was x squared minus 16, and don't forget the 1. So this then becomes this integral. When we do that, it becomes the integral of 1 plus a plus b. Remembering that this is a difference of two squares, you get x minus 4 x plus 4 dx. Once we've done that, we can get a common denominator, add the factors, and then equate the numerators, and then what we get is the numerator is now 15, so 15 equals a x plus 4 plus b x minus 4. When we do that, we choose numbers which make one of these equal to 0. So we have x equals minus 4 in the first instance. So minus 4 plus 4 is 0, so that will get rid of this expression, which is left with b. So b minus 8 equals 15. So b then equals minus 15 over 8. then if we have x equals 4, a8 equals 15, and a equals 15 over 8. Sometimes it's usual or useful to use x equals 0 as well, and that will get rid of a certain number of factors, and then we can work out the unknown factor. Anyway, let's get on with this. So this then becomes the integral of 1 plus 15 over 8 x minus 4 plus minus 15 over 8 x plus 4 dx. And when we do our integration, it becomes integral of 1 is x plus, then we gather our 15 over 8 to one side, so factor the 15 over 8 out, and we get natural log of x minus 4 minus natural log of x plus 4 plus c. Got integral of x squared plus x minus 1 all over x squared minus 1 dx. This then becomes the integral of, again, the numerator plus x minus 1, but in the denominator we can see we've got a difference of squares, so that's x plus 1 x minus 1 dx. This then becomes the integral of a over x plus b x plus 1 plus c x minus 1 dx. Then, after getting common denominators, adding the fractions and equating the numerators, we get the numerator x squared plus x minus 1 equals a x minus, or x plus 1 rather, x minus 1 plus bx x minus 1 plus cx x plus 1. So if we let, in the first case, x equals 0, a equals 1, x equals minus 1, b equals minus a half, and when we let x equals 1, c equals a half. And then when we put it back into our equation and then integrate it, we get the natural log of x minus a half natural log x plus 1 plus a half natural log of x minus 1 plus c. Let's have a look at a similar thing but with repeated factors. So we're going to have done that one. So if we have integral of x plus 7 over x squared x plus 2 dx. So here we have a repeated linear factor as the x squared. So this becomes integral of a over x plus b over x squared plus c over x plus 2 dx. Then when we get the common denominator, add the factors and equate the numerators, we get ax x plus 2 plus b x plus 2 plus c x squared equals x plus 7, which is the numerator. When we put in x equals 0, we get b is 7 over 2, x equals minus 2, we get c equals 5 over 4, x equals minus 1, a equals minus 5 over 4. When we put these back into our equation here with our factors rate, we get minus 5 over 4 natural log of x, which would be the a over the x, plus b, which would be 7 over 2 natural log of, no, this is not a natural log, sorry, because it's x squared, so it'd be x minus 1 over minus 1 plus 5 over 4 natural log of x plus 2 plus c. So just that little x squared when we're integrating, to watch out for it.